Hello everybody. Today we talk about the depletion layer analysis. Depletion layer within silicon are extrinsic silicon created by p-type and n-type is a basic of the old devices in the semiconductors. The diode, transistor, MOS, everything come from here. So this is a very basic equation you have to go through. And what is a depletion layer? Depletion layer is, okay, when you add the plus and minus for this p-n junction, what happened is a carrier move, say all the n-type carrier move this way and p-type carrier move this way. In the middle there is a depletion layer, so there's no carrier. And remember the previous video I explained conductivity depends on the amount of carrier, and next is the mobility. It's like a resistor, right? And space charge. Okay, and this amount of carrier is related to space charge. What is space charge? When you have this kind of depletion layer, then you have space charge, negative charge here, and the positive charge here. So what's happened? Internally, there will be electrical field this way, right? And that means when electron is injected from negative electron need to go against the electrical field. If you reverse the polarity both way and this is positive E, you're going against electrical field. So this is a effect of space charge, and there's no carrier here. So basically it's become insulator, right? And insulators, you still apply the voltage, then can we make the current going through? You have to go against this electrical field created by space charge. Okay, that's the effect of depletion layer, and we use this over and over for diode, bipolar transistor, and MOS. This is the basic of semiconductor, so you have to go through this theory. Now you know two types of intrinsic silicon is form the junction. You have a Fermi level, and this is a p-type, and n-type. There will be band gap is an intrinsic 1.1 electron volt all over. Okay, so let's see. Here's the center of energy. Go here. There will be a difference here, and this is going to be negative Q phi P, depend on the amount of impurity. And here there will be Q phi n. Okay.
Yep, that's what we did in the previous video. And
Normally, impurity for P and N is
order of magnitude different. So you take only one side, and
from this is the equation
I wrote in the previous video.
Ni
And
Q phi kt. This D is a donor. Donor means you donate the electron. This acceptor is a hole. Ni E Q phi P. This is N kt.
okay,
So what Ni is the geometric average of the p-type and n-type impurity
density, right?
and usually if donor dominant, this equation is used. If acceptor dominant, then this equation is
Is used because the other one is going to be buried with
overwhelming amount of impurity.
from other side. Okay, so
From here you can get
this
phi n, which is kt over q log nd, donor impurity of
donor.
and I. This is like a phosphorus, right? And the other equation give you P, this is N, kt over q log Na and Ni. So we need to use only one side of equation because usually is Nd is, or Nd is much less than Na.
Okay,
So if you look at this voltage difference, so this is going to be say phi b
equals
phi n minus phi p, and n is this. So kt over q log Na and D and I square. Okay. So this is going to be the space, the electric field potential generated by space charging. This is a space charge here. Okay. So
this space charge.
we have to solve another equation we show in the previous video is
This Poisson's equation. Okay.
So this simplify to one-dimensional.
Okay, and simplify further. The
Rho
is the rho is the density
minus Q and A, or Q and D. That's the amount of charge existing in this area. Okay.
So this is the
negative charge density and epsilon. That's a
Poisson's equation. Now,
if we simplify, say this area
there's a
x nxa or xd, we assume there is a certain thickness of this space charge, and usually it's as I said, either this or this, so only one sided.
okay,
So in this case, this distance, the d,
equals square root of 2 pi
epsilon q and d, the same
equation we can get.
So we can estimate the thickness of this
Depletion layer. So once we know the thickness,
then we can calculate the this act as a capacitor, right?
and the capacitor
Is going to be, we go through, you know,
capacitor is C equals
this this capacitor, you have a distance,
this distance and
epsilon, that's a capacitor for this side, right? Using this one, you plug in the
capacitor we can calculate.
to V. Now, this we use only one side because depend on situation, NA, ND, or ND, NA. Okay. And why
Capacitor is important. The capacitor is
important in the device switching speed? So when you have a transistor, we create a transistor like N plus N, this is the collector, and P and N plus, this is N P N transistor, right? This is the base and emitter and the collector. Now we have a reverse bias here, so it has a capacitor here, right? And this also has a capacitor against, say, P substrate, and those capacitor is called stray capacitor. And when transistor switch on and off, this voltage change high and low. So when capacitor is large, it doesn't go like that, it's go like that, and when switch off, it's go like that, right? Because of the capacitor effect. So this capacitor is very important for device switching. The MOS is the same thing. You use P and N combination and reverse bias. Every time you reverse bias, there is a depletion layer. Depletion layer act as a capacitor. if you try to change the voltage of one side, you have to charge up or discharge from depletion layer, the amount of charge, and that's going to be very slow. In the MOS, you have only short amount of time to charge up here, and you're not charging up for device, you're charging up for this peripheral, they call stray capacitance. So that's why the MOS initially, when it came out, was extremely slow. The bipolar, you can pump up more current. Okay, for the large chip nowadays, the less current preferred, and speed can be increased by shrinking the device size, like 7 nanometer. Then capacitor become linearly decrease, and that's the way most speed up for large chip. Okay, so this capacitor is very important. Okay, now, so after all, diode characteristic of voltage and the current is going to be like that. Okay, and the father of semiconductor, the shock ray, made the equation that's fit with this experimental result. Well, the original equation he made is J, this is J equals Q dN NP the LP and E Q V over KT minus 1. So exponential equation is shifted to here. And what is this LP? First of all, dN is constant to curve fitting. All the equation we go through has assumption like depletion layer is flat, square shape and stuff. So you can't get exactly the experimental equation, so you need to adjust by some constant. So D is a constant, and LP and Ln is going to be d pi. Okay, so this equation shows when V is certain positive number, you can ignore this one and become exponential, right? But if you have a negative voltage, depletion layer created and the no more current flow, it's gonna be pretty much constant. This one disappear and become Q dN NP over LP, constant. So after certain negative voltage, it's going to be constant. But can you go constant all the way? Because what's happened is this depletion layer grow on the one side depending on which, okay, this is a P and N. As you increase the voltage, right? But some point it's breakdown. So actually diode become like that.
And most of the diode is it's a destructive breakdown. So inside the atoms positions change around. Okay, that's about 3 to 7 volt usually. Some of them is not destructive. So what happened is Zener diode is not destructive. It's go like that and has a certain voltage, say voltage, fixed voltage, F volt. So what we do is we use the Zener diode reverse biased, and this voltage varies, but this voltage is going to be F volt, fixed voltage. So we can get the fixed voltage from Zener diode using this part. If voltage try to increase, it doesn't increase because it's goes all the way, the current increase and RI increase and push down the voltage here. So this voltage becomes very constant. So that's a Zener diode. Okay, so some of them not destructive. And there is a tunneling diode. The tunneling diode is like this depletion layers stay narrow and suddenly it start passing this layer to flow the current. Why? Because the electron is wave, and the wave go over this area, and the probability of this side increase. So it's like an alien movie, right? It's passed through the wall, and that's a tunneling diode. Okay, so there are many type of diode existing. That's we are going to go through. And the MOS I think we have to allocate one video for this, so I think we will do it in the next video. Okay, if you like this video, please subscribe and click like. Thank you.